Okay, hello, my name is Mohammed Akira. I'm a PhD student in the Quantum Information Group at Atomic Physics, and I will be teaching you the spectroscopy lab. So you will go more in details in the theoretical part of the spectroscopy, atomic and the molecular spectroscopy, but I will just give a brief introduction of some theoretical background so that you have more idea of what we will be doing in the lab when you start working in the lab. So I guess so far you heard about the photoelectric effect, and you know that the main idea is that light is quantized. So you cannot have a continuous energy. It only comes in packets of energy called photons. And if we want to write that down, we can relate the amount of energy in a pocket or in a photon of a quanta of light as delta E is h times the frequency. So we're relating the energy to the frequency. And the frequency is related to the wavelength of the photon through the c over lambda. So in this way, we can, if we know what the wavelength is, we can know what energy this photon carries, and vice versa. So first, we will talk about the atomic spectroscopy. And you know that when the electron gets excited, consequently, it only moves in discrete ways from level to level. And that movement is like at the same time, it will be there will be absorption of a photon of one of these quanta of lights, and that how much light that will be absorbed depends on how much the gap is between the levels that the electron is jumping between. And the same way can be said if you have an excited electron in the atom, and then it will go back to the ground state or unexcited state. That will also be done discretely, and then it will be followed by an emission. And that's what we are looking at here. So here you see the different levels of the electronic structure, starting with the quantum number n, which starts from 1 and goes up to basically infinity when we reach the continuum. And yeah, so between each levels there is a certain difference in energy that the electron has to have or to release when it moves. So people have looked at the rules that control this movement of the electron, and they come up with different formulas. So you will look at the Balmer formula, which is a simplified or a special case version of a more general rule called the Rydberg formula, Rydberg-Rates formula. That if you know the initial state or the initial quantum number and the final quantum number, then you can know what is the energy, or through this relation, what is the wavelength of the photon that will be emitted. And so there are different series that people looked at. And each series is defined by, like, let's say that we excited the atom, and then it will be, the electron will be released or go back to one of the lower levels. Depending on what is the lower level is, that will be different wavelengths, and people call that series. So there's the Lyman series, and that is when the electron moves from one of the higher levels to the n equal 1 level. And what we will be working on, what will be interesting for us, is the Balmer series, and that is when the final state is n equal 2. And these lines are the lines that we will be working on. So we will excite a gas, hydrogen or mercury, and we will see the different lines as the atom or the electron goes back to the n equals 2, 3, 4, etc. And there are more series that we will not be interested, but it's good to know the Bakken series, bracket series, and as like each one is defined by the final state. So the formula that we will be using is very simple. So it relates the wavelength of the emitted light to the two levels. And in our case, you will know what are the two levels. So in the case of Balmer series, the final will always be 2. And then you will see the levels from in I equals 3 to 4 to 5 to 6. Depends on how good you're doing the experiment. And if we're looking at hydrogen, for example, the atomic number would be 1, and you will measure the wavelength. And knowing the wavelength, the atomic number, the levels that we are talking about, then you will be able to calculate the Rydberg constant. So that will be the rule, or what we need to do in this part of the lab. And one thing to remember, to keep in mind, is that we are working here in air. So the wavelength that you will be this formula calculates the wavelength for vacuum. And the wavelength that you will be measuring in the lab is the wavelength in air. So one thing that you need to figure out is how to convert between the two. There's a refractive index involved, but then, yeah, that's something to keep in mind. So now that's very general overview. The next part would be how are we going to do this experiment? Hello. So now we're talking about the setup that you will be working with for the atomic spectroscopy lab. And the setup consists of first a light source, which will be a hydrogen lamp that will have a voltage across it when you start the lamp, and then that will create some electron beam that will excite the hydrogen atoms, and then as the atoms de-excite, they will emit all kind of lights corresponding to different transitions to lower levels. And in this experiment, you will be focusing on the Balmer series, so light or electrons going from upper levels to the second level. So you have the light source, and then you have a filter, two of them actually, and these will be used to basically attenuate the light when needed. So depending on what line you're looking at, sometimes you want to have less light because it's too bright. After the filter, you have a slit that you can control the width. We're using this micrometer, and that you will not need to, you need to align it once, and then that will set how much background you have. And then you have the light transmitted through the slit and then reflected by the first mirror inside the box, which will just redirect the light into this mirror, which will reflect the light into the slits. So you have the grating, sorry. And the grating you have different gratings with different number of slits per millimeters. So you will work with two of them. One with 300 slits per millimeter and one with 2000 slits per millimeter. And each one will have different spacing between the slits, which means that you will have different wavelengths diffracted by different angles. So all the diffracted light will be collected or reflected by this focusing mirror that will focus it into this corner of the spectrometer. And in this corner you have two options. The first option, you can direct the light to exit through this hole here, and then you can use a lens to focus it into your eye. And then using that, you will just be able to see the different lines of the Balmer series by eye. So you will just see a darkness with some lines, colored lines corresponding to different wavelengths in the Balmer series. So that would be the first step, just to resolve the lines by eye. And then you know that everything is working. Once that is working, you will close the hole here to reduce the background, and then you will align the mirror here so that the light goes into the CCD detector. And the CCD detector will resolve the light so that it is collimated, so that each wavelength will be resolved at its corresponding angle, and then you will get a spectrum with how much intensity you have in each line and with wavelength. So the interesting and the fun stuff happen at the grating here, the part which create some interference that will lead to discrete lines that we will see later on the CCD camera. So it would be interesting to know how does that exactly work, and that we will show on the whiteboard. Okay, so we have the incident light coming in here into the grating, and then we have the refracted light at a different angle here. And then we're basically talking about some form of interference happening here. And the light that you will see here you will see because of this condition basically here. So you will see constructive interference on the other side when the phase is an integer number of 2 pi. And the phase here is related to the path difference between the incident light and the diffracted light. And yeah, I will not go in details here, but normally the phase is written as the multiplication of that distance times the wave number. And if you do the geometry of the rays here, you will see that x can be written as the slit separation, d, times the sine of the incident angle and plus the sine of the refracted angle. So if you put everything together, where the k, the wave number, also can be written as 2 pi over lambda, the wavelength, and x, and keep 2 pi times m, the condition for constructive interference, you rearranging that will give you yeah, the condition for constructive interference. And that is what yeah, that's what you can, if you know the incident angle, for example, and the diffracted angle, d, you can figure out, yeah, if you know some parameters, you can figure out the rest of the parameters. And here we know what is the d, the spacing between the slits. We know the incident angle, we know the diffracted angle, and from that the software will figure out what are the different wavelengths.
See you soon.